All right, we are going to continue talking about solving trigonometric equations today. And today we're going to look at equations that require factoring in some form. Maybe they're quadratic in form, or maybe they have a GCF or something that we can factor out. So that's what we're going to talk about today. I'm going to share my iPad with us. Let's see here. Do I have it? There we go. Okay. So what we are looking at is equations that are trigonometric in quadratic form first. So again, this does not mean that they are quadratic, because that would mean it would have to be a polynomial, but it does mean that they follow that quadratic form that's a times u squared plus b times u plus c. And in this case, u is going to be some sort of trigonometric function, and this first term can't be 0 because then it wouldn't be quadratic anymore. So we'll need to factor or maybe even use the quadratic formula to be able to solve these. The same idea that we did with exponential functions that were quadratic in form or log functions that were quadratic in form, we will go ahead and use some u substitution here to get it into a form that is convenient to work with. And then we'll go from there to solve and put our u's back. So I can tell that this first one, example 6, is quadratic in form because it is 2 cosine squared plus 1 cosine minus 1, which is a constant. Notice here again, we're looking for only our solutions on 0 to 2 pi. So that does mean that we have to make a list of all of our solutions here at the end. Oops, I'm about to spill more coffee again. Okay, so the thing that is being squared and the thing that is quadratic about this is the cosine. So I'm going to start by saying let u equal the cosine of x. If I remove all of my cosines and replace them with u, then my equation now becomes 2u squared plus u minus 1 equals 0. That's a quadratic function that we're very used to working with. So this one is factorable. Again, whatever method you use to factor is fine. So you might want to use factoring by grouping, or this is a great one to just guess and check. I know that to get 2u squared, I have to do 2u times u. And I know that to multiply to get 1, it has to be 1 and 1. Now, the question here really is I need my outsides and my insides to add up to positive 1u. And since my last term is negative, bell just rang, one of my 1's is going to have to be negative. So I want this one to be positive and this one to be negative. That'll give me positive 2u for my outsides and negative 1u for my insides, which is going to give us exactly what we want. Now, once we have this in factored form, then we set each factor equal to 0. This gives me that either u equals positive 1/2 or u equals negative 1. So now we've solved our quadratic. But remember, it wasn't u that we started with, it was cosine of x. So I can now rewrite this as cosine of x equals 1/2 and cosine of x equals negative 1. So by factoring, I've gotten this apart into 2 separate trig functions that I can work with much easier. Cosine of x is equal to 1/2 at pi thirds and 7 pi thirds. No, 5 pi thirds. 7 would be too big. And then cosine of x is equal to negative 1 on the this side of the unit circle. So it's going to be at pi. And we only want the solutions on 0 to 2 pi, so we don't need any plus 2 pi n's or anything like that. That is our answer. We've got both of them, okay? So take a moment and go to number 7. See if you can decide what u would be. Verify that this is quadratic in form. What would you make u equal to? And rewrite it in its quadratic form. I'll give you a second to go ahead and try that. So for this one, the u is the sine of x. I have sine of x squared, sine of x, and then a constant. So u equals the sine of x. That's going to make my equation 2u squared minus 3u plus 1 equals 0. And once again here, we're only looking for solutions on 0 to 2 pi. So this one is also factorable. I'm going to get 2u and u. And then these both have to be either both positive 1 or both negative 1, because again, I'm trying to multiply to get positive 1 there at the end. So since my middle term is negative, that means both of these need to be a minus. Now solve those equations for u, and then see if you can replace with your trig function and see what you get. So this one comes out pretty similar. U equals positive 1/2 or U equals positive 1. So, whoops, we're not doing cosine this time. We're doing sine. So either the sine of x equals 1/2 or the sine of x is equal to 1. Again, only looking from 0 to 2 pi. So once I get my numbers on the unit circle, I'm all done. So sine of x is equal to 1/2 at pi/6. So x is equal to pi/6 and then also quadrant 2. So that is 5 pi/6. And then sine is equal to positive 1. Anytime you've got ones and zeros, that's the corners of your circle. So y is positive 1 at the top. That's going to be pi/2. And there are our 3 solutions. Okay. Number 8 is also quadratic in form. It looks a little different because it's only got 2 terms, but you should hopefully notice that this is the difference of squares. 4 sine squared minus 1 is going to factor to be 2 sine of x minus 1, 2 sine of x plus 1, and that equals 0. So that is one way that you could do that, is by factoring. Again, if you wanted to let sine equal u and do it as 4u squared minus 1 to start, that is fine. You could also solve this one using square roots, but I want to make sure that you're really careful if you do that. If I'm going to use square roots, I would add 1 to both sides. So I get 4 sine squared of x equals 1. Then I would divide by 4. So I get sine squared of x equals 1/4. And now to undo that squared, I need to take the square root of both sides. Square root, square root. Do not forget that when you take the square root in an equation, you have to account for the plus or minus. So this becomes sine of x equals plus or minus 1 over the square root of 2. That's really plus or minus root 2 over 2. And so since we want all of the positive and all of the negative square root 2's over 2, our solutions are going to come from all 4 quadrants, the 2 positive quadrants and the 2 negative quadrants. So we will get pi/4, 3 pi/4, 5 pi/4, and whoops, I wrote sevenths. I was getting ahead of myself here. 5 pi/4 and 7 pi/4. There's our solutions. If you use square roots and you leave off the plus or minus, you're only going to get half of your solutions. We can see over here on the factored side that when I set each of these factors equal to 0, I'm going to get sine of x equals, what did I, oh, this is not going to be square root of 2 over 2. This is just 1/2. You probably caught that as I was talking, because sometimes you guys do better than I do. The square root of 1 is 1 over the square root of 4, which is 2, not the square root of 2. So we don't need to rationalize anything here. What we want instead is all the places where sine x equals positive 1/2 and all the places where sine x equals negative 1/2. These 2 points in the equation are doing the same thing. Just make sure that you do not forget the plus or minus here. Okay, so once I have that, all the places where sine is going to be 1/2, whoops, that's a highlighter, is going to be x equals pi/6, 5 pi/6, 7 pi/6, and 11 pi/6. Again, just looking from 0 to 2 pi. Okay, so those are the ones that are quadratic in form. Now, there are a couple of things that we have to watch out for. when we are solving these equations, okay? We're going to look at some where we just use some factoring of some other sort. It may not be because it's quadratic, but this note here is really important. There are values of secant, cosecant, tangent, and cotangent that are undefined. So since they're reciprocals, secant is going to be undefined anywhere that cosine of x equals 0, because the reciprocal of 0 would be 1 over 0, and we cannot divide by 0. So those are the things that we have to look out for. So if I have more than one trig function, that is typically where we're going to need to use GCF factoring here. My equation, like number 9, has a tangent and a sine in it. All right. So for this one, I want to get it equal to 0, just like with quadratics or polynomials. If I'm going to use factoring, I need them to multiply to equal 0. So I will start by subtracting 3 tangent x from both sides. That gives me tangent of x. Oops, I didn't mean to zoom this in so far. Tangent of x sine squared of x minus 3 tangent of x equals 0. Then I see that they both have a tangent of x. So I'm going to factor it out. Tangent of x times sine squared of x minus 3 equals 0. Now there's a couple of things weird that happen with this one, so pay attention to what we're doing here. Now that I have it factored and the two trig functions are in their own factors, I can set each factor equal to 0 to be able to solve this. So my solutions are going to come from either where tangent of x is equal to 0 or where sine squared of x minus 3 is equal to 0. Tangent of x is equal to 0 at x equals 0 and pi, okay? Now sine squared, I'd have to add 3. Sine squared of x equals 3, and then take the square root. Sine of x equals plus or minus the square root of 3. Here's what's tricky. Square root of 3 is about 1.7-ish, which remember, sine and cosine, their range values are -1 to +1. Cosine is -1 to +1 this way. So this value is too big, which means no solutions come from this equation. They're extraneous. That factor became extraneous. And the only two solutions we get are here. Okay. Now, there was no secants, cosecants, anything like that. And I found the values for tangent that do give me 0. So those solutions are great. But let's look at one final example where this additional function can cause some problems. So this one is missing an equal to 0 at the end. You can just add that in. So I noticed that those both have sine in common. So I'm going to factor that out. Sine of x times cotangent of x minus 1 equals 0. Set each of our factors equal to 0. So sine of x can equal 0, or cotangent of x minus 1 equals 0, which means cotangent of x equals 1. Okay. So sine is equal to 0 on the sides because it's not up or down any. So this one is going to be x equals 0 and pi. And the cotangent is equal to 1 when sine and cosine are the same. So that's when your x and y are the same, which means this will be at pi fourths and 5 pi fourths. Okay. Quadrant 1 and quadrant 3 are where they're both positive or both negative, square root of 2 over 2. All right. Here's the tricky part now. Because of this cotangent, we have to consider what the domain of cotangent is going to be. All right. Cotangent is going to be undefined whenever sine of x is equal to 0, which means both of these solutions are extraneous, because if I plug those back into the original function, cotangent would be undefined and this equation won't work. So those are extraneous solutions. It is just the same as with logs. If I have log base 2 of x minus 5 and I try to use x equals -1, we can't do that because we can't have a negative number inside the log. It's not in the domain. So this is extraneous. Here, if I try to let x equal 0 and I do cotangent of 0, that is undefined. So it will not work in the equation and we have to eliminate it. So the only two that are good are going to be these right here. So that's kind of a sneaky thing that we have to keep in mind. The GCF factoring, that is not the difficult part of these. It's when those functions that have undefined values show up and you need to check for extraneous solutions. But that is where we are going to go ahead and stop for today. The PDF is posted on Canvas. If you need to go back and recopy anything, feel free to rewind, rewatch, whatever you need. And I will see y'all soon.